Goeiedag. Sorry, yes. I prepared the presentation in Dutch. Sorry, I'll switch to English. That's no issue. I might not be so fluent in doing this right now because I all prepared it in my head in English. Sorry, in Dutch. So switching over now to the Intel presentation. Intel does a lot of things. You probably all know us from the silicon. We do make network adapters and stuff. But today what I'd primarily like to talk to you about is mission critical computing. And that's something you probably will encounter more and more, because that's also a trend we see, and also our colleagues from Red Hat also quite regularly talk to me about this. So in essence what I want to discuss with you today is basically what is mission critical, how do you define mission critical. I want to give you a quick update as to what is new in the architecture from Intel to basically enable mission critical systems. Also to do a little bit more discussion on what you can expect from mission critical enhancements in the platforms, and also how you can deploy mission critical systems in your infrastructure. So in essence, mission critical infrastructure, and traditionally when people hear mission critical they think about things like transaction processing, databases, business intelligence, or basically big databases. And you've probably seen also some white papers around from Red Hat themselves. They also do a lot of mission critical deployments for things like the Swift transaction processing. So any financial banking transaction is now primarily all done on Red Hat systems. And it's also kind of a level of sophistication where this can't go down because all financial payments go to the Swift system, and any moment of downtime you basically have a catastrophic failure in the finance system. So that system actually now also runs on Red Hat using mission critical Intel components. But mission critical, what is it really? Well, the traditional definition you see here is basically any kind of server or system that if it crashes, basically your company will be completely dead in the water, nothing will happen, you won't get any money, no revenue, your boss will call you angry, you might get fired even over it. That's the traditional definition. What you see nowadays, however, is kind of a trend is shifting. You know, how many of you can really function without an email still? You know, it's getting harder and harder. And if I ask my kids, for instance, you know, functioning without Facebook is kind of essential. So if you see it, you know, there's really a trend that more and more systems are becoming mission critical. Think about things like, for instance, CRM, finance applications, instant messaging, telephony systems, security, databases, storage, and yeah, to be honest, coffee machines, because that's something I just added in myself this morning because I had a kind of a frustrating thing when I woke up this morning and tried to get a cup of coffee. My coffee maker said it had to decalcify itself. So, and that thing takes about half an hour to get all the system laid out and before you can get some cup of coffee. So that was highly frustrating for me. It's also kind of a mission critical system for me. So in essence what you can say is that mission critical is more or less anything can become mission critical. It depends on what your needs are and what your requirements are. So mission critical traditionally been kind of the domain of high-end Unix-like systems. So things like IBM AEX, Solaris, you name it. It's been traditional, a big silo where you basically take the software, the hardware, all from one single vendor, and that's a mission critical deployment. However, recently there has been kind of a trend where you basically said, okay, this is a survey done by lots of different companies, of IT managers, and they asked in 2009, okay, how much downtime do we actually get from which server? What you see here, this is what they said in 2009, where they basically said, well, 2009 AEX and SUSE Linux, and we're all kind of with minimal downtime. However, in a recent survey, it really shows that you really make big leaps there, and basically saying that anything that runs on x86, okay, a few exceptions there regarding different OSs, has a very high reliability nowadays, and you can run almost anything nowadays reliable on x86. Well, that basically means that you can. It doesn't mean that, you know, if you buy the cheapest server that it will run reliable, but you know, there are provisions in the systems that can make it more reliable. And this is something I'm going to address here in my presentation further. So what are some of those innovations that have been happening lately? Well, one of the things you see here is, primarily you see here, is cause of unplanned downtime. About 20% of that is basically due to hardware OS failure or power failures. Other things, typically 40% is about operator error and 40% is about application failure. So although we primarily address this area, there are still lots of other areas that basically can get your system down when you're not paying attention to it. However, with recent innovations, things like new OSs, and I must say, I'll be honest, Hat Enterprise Linux 6 really improved an awful lot in this space. So with the availability of that, the level of mission criticality on an x86 system really went up. Other things like, well, the other thing is also more and more people are monitoring the systems, and you also see more and more x86 systems now being mission critically deployed. So we have more data available, and more people really start to get experience with it. So what do we see as this big shift that I announced earlier already? Well, traditionally, like I said, nowadays you see mission critical is primarily the domain of mainframe systems, and Epic RISC or Itanium systems, or Power, or Solaris, or Sun Spark systems, with just a little bit of x86. However, with some recent changes and some pricing changes, primarily in the RISC area, it's really become obvious that more and more people are saying, okay, we need mission critical, but we can't really afford to do it anymore on these high-end mainframe systems or those RISC systems. And now you see more and more people starting to evaluate x86 for mission criticality. And what you see probably in the future is that, well, the entire mission critical space will still be, occupied by some RISC Epic systems and mainframe systems, but more and more x86 will be doing its introduction into the mission critical space. And why that's doing, that's something I'm going to address shortly. This is really a little bit of what we see as the market trend going forward. These are the service sales. You see about 2000, Intel had about 36% the market segment share in the server segment, and 64% was RISC mainframe systems doing all the mission critical stuff. Today, nowadays, this is actually already all the data. In 2011, you see that really changing now. 61% is running x86, and more you see actually the RISC getting smaller and smaller. And for those who are really keen on numbers, here you see the total number of server growth as well. This is the server growth going from 2000 to 2011. You see that we have about a 340% growth in the amount of servers being deployed. But that's a little bit about all the market stuff and so on. We as Intel, we are great in building manufacturing chips. And just to get a little bit of perspective, this is just a single core there that we're installing, and it's not really actually to scale even. So this is something we do. This is not obviously not my picture, it's someone else in the factory. That's why he's wearing such a funny suit. This is what we call our bunny suits, and that's what people wear in the clean rooms. So mission criticality, how do you implement that on the platform? That's really can be kind of challenging. What you see here is that this is something that has been done already in the mainframe, in the RISC systems. And what they do is that there's an independent communication pod between the silicon system and the software, and it communicates back and forward to basically report things like error states, report things like how the system is doing, how it's performing, and also be able to make changes. So the software can talk to the silicon and make changes that way, and the silicon can modify the software. This is something that's now we initially piloted that on our Itanium line, and that's now being brought into the Xeon line of processors. And the current processors where you see it in is primarily the Xeon E7 line, so the higher line is where we have this system integrated. So what is this system? Well, to illustrate it, I have a short video, and I hope it works out of this thing embedded, and otherwise I hope it doesn't play this way. Let me go back one slide and I'll put all the VLC in. Okay, this is a short demonstration on what happens when the mission critical OS is deployed. Here you see two systems, and obviously it's running Windows because Windows fails a lot. And what you see here, I have two identical systems. One I have the mission critical functionality enabled, the other one disabled. And what I do is I inject a memory error into the system. That's something we can do via what we call an in-target probe, where we directly write to memory and we can corrupt the memory location. And what you see here on the right is, well, it's just running, but when I injected an error, basically the system detects, okay, yes, there's an error, it gives you a pop-up message or it lost a system event, and basically continues to function. Sorry, let's now into the next video, which wasn't supposed to do. Let me go back to the presentation. So what it actually does is, one thing, if you inject a memory error, normally normal behavior would be to say, okay, if it's a single bit error, typically the hardware can correct it. With more complex memory errors, yeah, the OS is losing control of the system, and as such, you get a memory corruption and you get a blue screen of that, or a purple screen in case of VMware, or a kernel dump in case of Linux. With this machine tech architecture, we can basically disable this functionality and basically say, okay, yes, we have an error. We can work together with the OS saying, well, this page in memory got corrupted. Typically, it might be that it didn't even get to use that page in memory, and as such, the OS can continue to function and just mark the memory area as bad and continue to run. If it doesn't, that's something you can prevent on almost any system. However, you need to have a way of reporting back from the hardware to the OS saying this is what's happening. And that's something what we implement with the machine tech architecture. And this is typically how this works. This is a short cycle. This is a continuously running loop of the system, and it continuously does things like repair errors if it can repair them, recover from those errors, minimize the planned downtime. So if you have an error and you have, for instance, memory corruption, you can basically say, okay, I disable this memory correction, this memory area, and continue to function. You may create a system log, and then later when you have some time, you can basically open up the system and replace the memory, or even do a hot swap of the memory in case your system supports it. It also can do things like prediction of failure, so it sees a kind of a trend happening that more and more memory starts to fail. It could contain those errors and basically continue to function. So how does it actually work? Because this is a nice diagram. This shows you a little bit more into detail what's happened when an error is detected. So you have a normal status, the system runs, and then all of a sudden something happens. Be it a PCI error, be it the system corruption, someone basically walked by with a cell phone and the shielding wasn't perfect, and as such some strange things happen in the system. So as soon as an error is detected, it can go either one or two ways. Either the hardware can correct it already, and that's really an easy thing, and basically you get an error log and that's it, it continues to function as normal. Or it's an uncorrect error. And in that case, a normal system would say, okay, die in panic, I don't know what to do anymore. But with MCA, you basically can contain that error and basically take some action in cooperation with the OS, do a complete recovery, and then have the system continue to run in a normal operating state. So what are some of these errors that we can contain? And this is a list of systems that is about a year ago, what we have for error-wise. Things you see here is different system buses that can be corrected. Memory can be monitored, you can do failover. What are things? Yeah, basically it's a complete system where any kind of error can report into. And what you'll see also is with newer processors coming along that we add actually more error detection and error prevention capabilities to new processors. So I mentioned already that it's a cooperation between OS, even maybe hypervisor, and the application. So what it does is, here's actually you see a list here also already of the OSs that support this MCA recovery capability. You see here it's Windows primarily, Red Hat Enterprise 6 does fully support it very well. Solaris supports it, SUSE, but also things like hypervisors. So you can imagine if you have a very big system, currently we can deploy systems with up to 4 terabytes of memory, and you start doing virtualization on that. Yeah, although you have virtualization and you can recover a single VM pretty quickly by failing over from one system to the other, if you have this entire 4 terabyte system and you have a few hundred VMs running on that, once that crashes, it takes maybe even up to an hour or even more to basically restart the system and completely have all the VMs up and running again. So, this really is an awful lot of downtime. If you want to have high availability, and typically what we talk about high availability is more than 5 nines availability, you're talking about a maximum of 5-minute downtime a year. So if you can imagine if you need to do a reboot and all these systems have to start, you basically already are over at 5 minutes, and your users will start to complain saying, hey, why is my system down? I can't work anymore. You lose money if you basically are down more than 5 minutes. So what happens here in the case of a virtual machine hypervisor in there, as soon as an error is detected, and let's take the memory error again as an example, as soon as that memory error is detected and the memory is occupied by a VM, normally the hypervisor would crash completely and all your VMs die. But now it says, okay, this area is only occupied by this VM, and then what it does is basically triggers a reboot of that VM and the rest continues to function. That's the case if the memory is occupied. If the memory isn't occupied, the hypervisor will still continue to function and just basically mark the area as bad and not assign it to any VM. So this really gives you a high availability there. And the nice thing is it's not only supported in VMware, but also Red Hat's KVM system or the virtualization products of Red Hat, the RHEV versions, also fully support this functionality already. The other thing is SAP. As SAP, that's more of a database application, and some of you might be aware that SAP is very actively developing their own database now. Probably because they had some issues with Oracle or so on. That's not officially what they say, but you know the trend might definitely be there. So one of the databases they've developed is something called HANA, and HANA is something that's called a complete in-memory database. And that's also something that's actually made possible by the fact that nowadays we can have lots and lots of memory in systems. Right now with the current 87 processor we can have the 4 terabytes of RAM memory in a system. And by having this entire database running out of memory, it gives you extremely good performance. This is really going from multiple minutes of query time now to a few seconds at most. And what SAP does actually, by having everything in memory, it's very nice, it's very fast, but you know what happens if you have a memory failure in that case? You know, you can have database corruption from here to wazoo. So actually SAP worked together with Intel also to integrate this MCA functionality at the application level in the database. And that's what my next video is about, when we already got the slide preview from. Let me just bring it up again. So here you see an SAP application. This is SAP HANA. This is one of the initial versions. You see it running here, and what I here have is a query window. And this is a list of tables I have in memory. And what you see here is basically I can trigger off different queries, and I can also basically select the table and completely kill the resource. So what happens here is that I do a query, and you see it basically takes about 1 second to run this query. And you see it again. So what I now then do is basically I select one table and I say, okay, kill this resource. And what I do is basically I inject an unfixable memory error in that location. I do the query again, and what you see is, yeah, it takes a little bit longer, but I don't see any kernel dump or kernel panic or system crashing. What you basically see is the system continues to function. It takes a little bit longer, in this case about 10 seconds, but what it does, it completely recovers data and there's no corruption of the database happening whatsoever. And this is technology with this MCA architecture. This is made possible by the MCA architecture. And this is something, a new functionality that SAP only can offer now because of the fact that we have this MCA architecture. And now here another mission critical thing happening outside. So what is this mission critical ecosystem already? Well, one of the nice things is now that we have enabled it in x86, we see all the mission critical development actually completely shifting away. Where it used to be in proprietary Unix systems where all the mission critical development now is done, it's now primarily shifting. Every new development that happens in mission critical space is happening on x86. And some of the vendors you see here are actively developing in this area. So server-wise, you can get mission-critical servers nowadays from HP, from Dell, Cisco, Fujitsu, Oracle, you name them. They all supply this mission-critical capability servers. You can get different operating systems with different levels of support. And I must say, Red Hat right now is one of the better supported functions. That basically almost every function that we can detect with MCA is being handled by the Red Hat OS. Virtualization-wise, also different vendors are supporting this. And also at an application level, different database systems also support this MCA architecture already. And higher level wise, other application layers on top also are supporting it, and more are being added every day. So, well, this is nice that we have this list, but you know, what happens in the real world? You know, are people deploying this? Well, this is kind of an illustration of the new capabilities you have. Going from Red Hat 5, Enterprise Linux 5 to Red Hat Enterprise 6, you see that there are lots of improvement made in the available memory that can be addressed, availability of systems, and basically lots of enhancements were made in that. And not only we saw that, and Red Hat saw that, but also several different companies. And I have here a few of them, companies like Lilly, which is an American company, 3M, Gap, the clothing company, China Telecom. They all basically saw that and basically implemented the system using mission critical architecture and Red Hat Enterprise 6 and basically made some interesting innovations. Here you see the different innovations they made. So for instance, Lilly, the pharmaceutical company, got a 40% increase in performance by going from proprietary Unix to the x86 architecture. And they come from a system from IBM, which is actually running at a very high clock frequency. The IBM Power is running right now at 5 GHz. Yet they go to an x86 platform, which runs at about 3 GHz, and still they get better performance. 3M. Basically, they got down to that they wanted to consolidate the entire mission critical infrastructure, and they reduced the amount of servers they had deployed for mission critical deployment by 25%. Cap made extremely significant savings in cost by implementing this mission critical infrastructure. Got a question or? Okay, so that's mission critical at kind of a theoretical level as to how we implement it in the processor. What happens at the system level? The system level, this is kind of a block diagram of how a big E7 system looks in the inside. You can have 1, 2, 3, 4, or 8, or 64 processors, however you want. But this is the basic architecture. What you see here is that you have multiple redundant buses. So, for instance, if this processor, this bus fails, there's always a different path to the same I/O component. If this memory fails, there are different ways of accessing that memory failure. Each processor can communicate with each other via different hubs. So the path, the length of communication might change, but there's always a secondary or a third option to basically continue to function. And that's also one of the capabilities that is kind of new to the platform, so we have redundancy built into the platform natively. So if one of the things fail, and also the buses themselves are self-healing, the memory channels are self-healing. It's a very extremely robust system, so hardly anything can bring it really down. What happens actually, for instance, if one of these system buses fails, so there's, you can have it function at full speed, full width, but if you detect a failure, so there's a short circuit or there's some other failure happening in the system, we can basically change dynamically the width of that bus, so the bus still continues to function, but you just have a little bit less bandwidth on it. And that's something that really also allows you to have a lot of better uptime capabilities in the system. Same thing goes for memory. Memory is a lot of parallel data lines, and what you have there is one of the data lines fails, and typically that leads to memory corruption. Well, the bus to the memory buffer is also very resilient. If one of the lines fails, it automatically can take over into a standby lane, and if the standby lane fails, then it can also switch over to error correcting lanes. So that means there's an awful lot that needs to go wrong before you get the memory corruption this way. And even if you get a memory corruption, you can basically fail over from one memory location to another. So there's an awful lot of things that need to go wrong before you really can corrupt something in here. One other thing that's new, and that's something that will probably come in a newer version of Hat Enterprise. Sorry, that was a question?
Yeah. Am I correct if I see these diagrams that you're switched to distributed memory?
The question is if you've correctly seen that if you switch it to distributed memory, it's yes and no. It really depends as to how you architect your system. The system itself, every CPU has their own memory bank. That's also how we get scalability. The more CPUs you add, the more memory bandwidth you get. If you configure it this way that you can have a mirroring going on, so you can actually distribute your memory load, and you can also distribute your application and migrate it from one processor to the other. That's all happens in a complete NUMA architecture. So when you have the system transparently as one big system, that's when you basically are able to switch over from one CPU to the other and have a higher uptime. One other functionality you have, and that's something that's relatively new, is something called hardware partitioning. And hardware partitioning is might be new to many of you. That's something that also comes forward from the high-end Titanium line, where we have lots of CPUs in one single system, but we can basically say, okay, this CPU, this memory bank, this I/O component, all are one system, and it's a complete hardware-wise, physically separated system. And how we do that is basically by those high-speed links that are in between the CPUs. These are programmable and disabled. So I can basically say, okay, I disable the link between CPU 1 and 2 here, and CPU 3 and 4, and as such, this is one system, and this is one system. And you can also do it on a single level. It also allows you to do things like if you have a higher license you need to pay for a big system like this. If you have a system like this, you can have up to 80 cores in that one system. If you need to pay Oracle license fees, for instance, the more cores you have, the more you pay. You can say with this, yes, I want the high availability, I want to run on this big system, but I don't want to pay the high license cost. In this way, you can say, okay, well, I run just on one CPU, and if this entire thing fails, it can very quickly fail over from one side to the other, and you can still even copy things like memory location over from one end to the other, and still continue to run. So that's something that's new, and that is something that we're developing in cooperation with HP. And I have some more slides on that later. And that's a new capability that you'll see probably coming in Hat Enterprise 7. I'm not sure if that's, I'm looking at Frank if he knows about that already, or no? Okay, so we're not making any statements about that yet. But that's something that's really under investigation. So, we talked about it already, and you saw already that mission critical. Oh, there's another question?
You say the hardware partitioning is advantageous to running Oracle applications?
No, not necessarily only to Oracle. Oracle can make use of it, and Oracle has a licensing system that is basically your pay per core.
But does Oracle actually support this hardware partitioning?
Yes, it does, on Oracle Linux. And that's why I'm saying it needs to be in Red Hat pretty soon as well, but yeah, it's a certification issue. So the technology is there, and it's something that's not that completely new. Like I said, we have it already on HP UX. Other risk systems also have this system one way or the other architected. It's a capability that's there already. However, we're now bringing it to the x86 platform. So, well, we talked about the platform now. Let's talk a little bit more about systems and how you deploy these things. One of the things that you might wonder is, you know, I have this high availability system and so on, but why does a Linux system fail? Well, this is a slide I borrowed from my friends at HP. Oops, sorry. I pressed the wrong button. So things like human error and so on, yeah, these are kind of obvious areas why a system can fail, but also things like this. This is what's kind of obvious to me, not so obvious to me as well. This example here, if you have a system and it runs out of memory, the kernel starts running kind of out of memory killer process. And what it basically does, it seeks the biggest memory consumption thing, memory consuming application. If it's an Oracle database, for instance, it can completely kill off your Oracle database to continue and have the system up and running. It's an interesting behavior, and in some cases it's great to have the uptime of the system, but you know, if you have your mission critical Oracle database killed this way, it's not such a good thing. So you might want to have provisions for that as well. Other things like hardware failures has kind of similar behavior, but the one thing is, you know, you need to architect a little bit further than just the one system to have a real mission critical deployment. And that's where we work together with our guys from HP. Well, you know, we make the source mini chips. HP, although we work together with them also on some of the chip designs, HP primarily develops systems. And that's actually, this is what we do. Sorry, I went ahead a little bit. This is very, very good then. Our slide, this is our production technology, and like you see, well, we have chip technology up to wazoo for the next 10 years. You guaranteed to see newer, faster chips from us. HP does primarily this. Where HP primarily, the mission critical initially was only on HP UX with Titanium. They're now actually switching over and say, okay, with the same systems we have built, we can now basically deploy the same infrastructure on HP UX and x86. And they're starting a real gigantic project called Project Odyssey. And Odyssey is primarily because of the long journey they think they have for it. And I must say that they've been already doing quite a good job with it. And what I've done here is primarily things like all the features they have, things like always-on resiliency, things like dynamic optimization. So you have a mission critical system running, but all of a sudden you need more memory. You have a one partition. That one partition isn't enough anymore. You want to online add a secondary partition to that. So you can add online a secondary CPU or more memory, or even a third or a fourth CPU to the system. That's something that HP is bringing to the table, and that's something they've been doing it for years. They have quite a lot of experience in it, and they're actually doing a pretty good job in it.